Hello viewers, in today's lecture we are going to take up a very important topic in maxima and minima, and the topic is point of inflection. Now in our earlier videos we have already discussed the concept of increasing and decreasing functions and the concept of maxima and minima, right? In those videos we have also discussed the concept of point of inflection, but here I am making a separate video on this concept of point of inflection. So before starting this concept, let me clarify the meaning of some important terms just for the sake of revision. Now let us take the term critical point. So points on the graph of a function where the derivative is 0 or the derivative does not exist are very important, right? Suppose we have a function y equal to fx. Now if we differentiate this function, we get the derivative f dash x or f prime of x. Now if the derivative is equal to 0, then from here we find the critical points. Now here we see that the point x comma y, is called a critical point of this function f of x if x is in the domain of, let D be the domain, and if x belongs to the domain of this function, and if we have either the derivative is 0 or the derivative does not exist. It means it is undefined, right? Now let us take an example, right? We see that this is the absolute value function y is equal to mod of x, and the graph of this function it looks like, see, this is the graph of y is equal to mod of x, and we see that this function is continuous. This function is continuous at x equal to 0, but it is not differentiable. It is not differentiable at x equal to 0, right? Now by the definition of critical point, points on the graph of a function where the derivative is 0 or the derivative does not exist. So here in this case of absolute value function, the derivative does not exist at x equal to 0. So therefore x is equal to 0 is a critical point, of this function, of the function y is equal to mod x, right? Similarly, if we have a function say y is equal to fx is equal to mod of x minus 2, then we see that this function is continuous, but this function is not differentiable at x equal to 2, right? So it means f prime of x does not exist for this function at x equal to 2. So therefore x equal to 2 is a critical point of this function, right? So therefore we can say that the critical points occur when the first derivative is 0 or it is undefined. Now let us take these two graphs. Now here we see that this graph it increases from point A to B, and then it decreases from point B to C. And here when we see this graph, we see that this graph decreases from point D to point E, and then it increases from point E to point F, right? At these points, at point B and E, we see that the derivative is 0 and the tangent is parallel to the x-axis, right? Clear? So here we see that the point x is equal to a and point x equal to b are the critical points. Clear? And here this point b is a point of a local maxima, and here the point E is a point of local minima, right? So here in these two graphs we see that when this point P is a point of local maxima, then the tangent or the slope of the tangent, right? See, this point is a minus h, here this point is a plus h. Similarly, here we have b minus h, and here we have b plus h. So this is the point A, and here we have a minus h, here we have a plus h. Similarly, here we have b, this is point b minus h, and this is point b plus h, and in both cases h is greater than 0. So these 2 points are in the neighborhood of point A. Similarly, these 2 points are in the neighborhood of point B. Now we see that at this point a minus h, the slope of the tangent is positive, right? So here the slope, that is f dash x, is positive, and at this point the slope becomes negative, right? Similarly, here the slope at this point, that is b minus h, is negative, and at this point the slope is positive, right? So when the function moves from this point A, from a minus h to a plus h, we see that the sign of the derivative changes from positive to negative. So x equal to a is the critical point, and the function attains local maxima. Similarly, when the slope of the tangent or the derivative changes sign from negative to positive, when the curve passes through point x equal to b, then this point x equal to b is a point of local minimum, and at this point E, the function attains local minimum, and x equal to b is a critical point, right? So in these two cases we see that the derivative is 0 at these points, and this point and this point, right? And the curve the derivative changes sign when we move from this point to this point and from this point to this point. But in some cases we see that the function the derivative does not change sign, right, when the curve moves from one point to another. So in that cases the derivative does not change sign, and such a point is known as the point of inflection. Right? Now viewers, we have just seen that there may be some points where the derivative does not change sign, right? Now a critical point is an inflection point if the function changes concavity at that point. Now let us see the concept of concavity. So what is meant by concavity? Now here a graph is said to be concave up. A graph is said to be concave up when the tangent line is below the graph. For example, see, in this case and in this case the tangent line is below the graph. See, this is the graph y is equal to f of x, and this is the tangent line, right? This is the tangent line, and such a graph is called concave up. Concave up. So a graph is said to be concave up if the tangent line to the graph lies below the graph, right? And here also we see that the tangent line, this is the tangent line, and this tangent line lies below the graph, and this is y is equal to f of x. So this is also concave up. Now in these two cases we see that the graph is this is the graph y is equal to fx. Here also this is y is equal to fx, and these two are the tangent lines. This is the tangent, and again this is the tangent, and we see that the tangent line lies above the graph, right? So this is called concave down, right? This is called concave down, and here also it is called concave down, right? So a graph is said to be concave up if the tangent line which we draw to the graph, it lies below the graph, and the graph is said to be concave down. Here it is concave up, here it is concave down if the tangent line lies above the graph, right? Now here we see that this is the tangent line, and let this is angle theta. Here it is say this is theta 1, this is theta 2, this is theta 3, and here see this graph, this tangent makes angle theta 4 with the x-axis, right? Now in this case we see that the slope is positive, that is f dash x is positive, and here the derivative is negative, and here also the derivative is negative, and in this case also if we extend this line further we see that we'll have the angle theta 4, and the derivative will be positive, right? Okay. Therefore in this case we have this function as concave upward increasing, right? Because the derivative is positive. And in this case the function is concave down and it is decreasing. In this case again the function is concave up, but in this case the function is decreasing because the derivative is negative as the slope is negative, right? And similarly in this case the graph is concave down, but the graph is increasing as the derivative is positive. Okay, we know that a function is said to be increasing if the derivative is positive, and the function is said to be decreasing if the derivative is negative, right? So therefore a critical point is an inflection point if the function changes concavity at that point. Now let me take a very interesting example. Now inflection points are points where the function changes concavity, and we have just discussed the meaning of concavity. A graph is said to be concave up when the tangent line is below the graph, and the graph is said to be concave down when the tangent line is above the graph. Now here we have a function f of x equal to x cube, and let us draw its graph, and the graph looks like, see, this is the graph, and here we have this type of graph, right? Now this is y is equal to x cube, and see, if we differentiate this function, we get 3x square, and if we differentiate it further, we get 6x, right? Now here I would like to mention the method of finding the point of inflection, and the point of inflection can occur where the second derivative is 0, right? So how to find the point of inflection? So point of inflection occur where the second derivative is 0, that is f double prime of x is 0. Now here we see that f double prime of x is equal to 6x, and for point of inflection, that is for point of inflection, the second derivative should be 0, so 6x equal to 0 and x is equal to 0. Now here x is equal to 0 is the point of inflection, but here I would like to tell you that even if the second derivative is 0, we cannot say that there is a point of inflection, right? So it is not necessary that if the second derivative is 0, and if we solve this equation, that is f double prime of x equal to 0, and we get the values of x, even if we cannot say that the values of x or the values so obtained are the point of inflection, right? So we can find the inflection points only if we analyze the second derivative, and let us see how to analyze the second derivative. Now here we have the function, and we have obtained the first derivative, this is second derivative, and for obtaining the point of inflection we have equated the second derivative equal to 0, 6x is equal to 0 and x equal to 0. Now let us analyze whether x equal to 0 is a point of inflection or not, because in every case, or whenever if we substitute f double prime of x equal to 0, then even the second derivative is 0, we cannot say that there is a point of inflection. So let us analyze it. Now what we will do, we will take this is x equal to 0, and we will take 2 points to the left and right of this point. Say to the left this point is 0 minus h, and to the right it is 0 plus h, and here h is greater than 0. Now we will find the sign of the second derivative at these 2 points, right? So at x equal to 0 minus h, let us find the sign of the second derivative. So f double prime of 0 minus h is equal to 6 times of 0 minus h. So here we have substituted x equal to 0 minus h. So this is minus 6h, and since h is greater than 0 or h is positive quantity, so the second derivative is negative, right? Because h is positive and here we have negative, so we have the second derivative as negative. Now let us analyze the sign of this second derivative at this point. F double prime, we have 0 plus h. Now we have 6 times of 0 plus h, and here we have 6h, and h is a positive quantity and 6 is positive, so we have positive. So viewers, here we have a very important conclusion. The conclusion is that x equal to 0 is a point of inflection because the derivative changes sign from negative to positive, right? From negative to positive. And here we see that uh, at this point 0, because this is the point x equal to 0 here, and in this third quadrant um, the graph of the function is concave down. This is concave down, and in the first quadrant the graph of the function is concave up. So here the graph of the function is concave down, and here the graph of the function is concave up. Therefore the concavity of the graph changes, right, at this point x equal to 0. Hence this point x equal to 0 is a point of inflection for this curve y equal to x cube. Clear? So inflection points are the points where the function changes concavity. So here in the graph of this function shows that it is concave down, and here the graph of the function shows that it is concave up. So the concavity changes, and x equal to 0 is a point of inflection, right? And further we have obtained the second derivative, and in the vicinity of x equal to 0, or in the neighborhood of x equal to 0, we have taken a point to the left and a point to the right. To the left we have 0 minus h, to the right we have 0 plus h, and we have analyzed the sign of the second derivative. So at x equal to 0 minus h, the sign of the second derivative is negative, and at x equal to 0 plus h, the sign of the second derivative is positive. So the sign of the second derivative changes from negative to positive. Hence x equal to 0 is a point of inflection, right? Similarly, if we have the sign of the derivative and it changes from positive to negative, then also we have the point of inflection, right? Thus we can say that whenever the sign of the second derivative changes from negative to positive and from positive to negative, then we have the point of inflection. But when the sign of the second derivative doesn't change, then we cannot say that this is a point of inflection, right? So we have concluded that even if the second derivative is 0, we cannot say that there is a point of inflection, right? So to decide whether a point is a point of inflection, we have to analyze the second derivative, and by analyzing the second derivative, it means we have to check the change of sign of the second derivative at the given point, right? Now here we have taken the 2 points to the left and to the right of 0 as 0 minus h and 0 plus h, but viewers, we can also assume these 2 points as minus 1 and 1, right? Because we have to test the sign of or we want to know the sign of the second derivative to the left and to the right of this point x equal to 0. So here I am taking just for example minus 1, because minus 1 is less than 0 and 1 is greater than 0. So let us take the find the values of this second derivative at this point and at this point, right? So here we have f of double prime of minus 1 is 6 times of minus 1, that is minus 6, and here we have 6 times of 1, and this is equal to plus 6. So here we are only interested in the sign, not in the numerical value. So we see that the sign of the second derivative changes from negative to positive. As we move from left, to the right through x equal to 0. So therefore x equal to 0 is a point of inflection. So this is a point of inflection. Now viewers, let us take this function and we have to find the point of inflection, right? To find the point of inflection. So what we will do, we will find the first derivative, and the first derivative is 6x square minus 12x plus 6, right? Now we will find the second derivative. It is 12x minus 12, and this 12x minus 12 can also be written as 12 times of x minus 1. Now for point of inflection, what we will do, we will equate the second derivative equal to 0, and this implies that 12 times of x minus 1 is equal to 0, and we get x equal to 1, right? Now here we have obtained the roots of this equation, that is f double prime of x equal to 0 as x equal to 1, and let us test, or let us analyze whether this point x equal to 1 is a point of inflection or not, right? So what we will do, we will take here x equal to 1, and we will take a value which is less than x equal to 1, and one value which is greater than x equal to 1, right? So let us take here x equal to say minus 1, and here let us take x equal to 2, and let us decide the sign of the second derivative at these 2 points. So at x equal to minus 1, which is actually less than 1, this point, and the sign of the derivative at this point minus 1 is 12 times minus 1. Here we have minus 1. Here we'll substitute the value of x as minus 1. So we have 12 times minus 2. This is minus 24. Here we are not interested in finding out the numerical value. We are interested in only the sign. Now let us find the sign of the second derivative at this point, that is at x equal to 2, which is greater than 1, and here f double prime of 2 is 12 times 2 minus 1, and we see that it is 12 into 1, and it is 12, and here we have plus sign. So therefore we see that the sign of the second derivative at x equal to 1 changes from negative to positive, right? Negative to positive. So therefore x is equal to 1 is a point of inflection, right? Now viewers, let us take this function, and here we have to find the point of inflection if the point of inflection exists, right? So what we will do, we will find the first derivative. First derivative is 3x square minus 3, and the second derivative is 6x, right? Now for point of inflection, we see that the double derivative or the second derivative should be 0, and here we have 6x equal to 0 and x is equal to 0, right? Now here we get the value of x as 0, and now here we have x equal to 0, and we will take 2 points, to the one to the left and one to the right, and let us say here minus 1, and let us take here 1, right? And let us see the sign of the second derivative. Now at this point the value of the second derivative is 6 times minus 1, that is minus 6, and here at this point we have 6 into 1, that is plus 6. So here we see that the sign of the second derivative changes from negative to positive, and hence x equal to 0 is a point of inflection, right? So therefore the sign of the second derivative changes from negative to positive, therefore x is equal to 0 is a point of inflection. So viewers, always remember, the point of inflection can be obtained by putting the second derivative equal to 0, and if we solve this equation we get some values of x. In this case we have x equal to 0, then take 1 point to the left and 1 point to the right of x equal to 0, and calculate the sign of the second derivative at these 2 points, right? And if the sign changes, then the given point is a point of inflection, and if the sign doesn't change, then the point is not a point of inflection. Now viewers, let us take this problem. Here we have the function f of x equal to x raised to 4. Now the graph of this function is plotted here, and this is the graph of f of x equal to x raised to 4. And see, the graph of f of x equal to x square is plotted here, and see the difference between these two graphs, right? Now here our aim is to find the point of inflection of this function, right? And if they exist, now we'll differentiate this function and we get 4x cube. Now differentiating this function, we get 12x square. Now the point of inflection can be obtained by putting the second derivative equal to 0, and this is 12x square equal to 0, and we have x square equal to 0, so we have x is equal to 0. Now let us see whether x equal to 0 is a point of inflection for this curve or not, right? For this we have to find the sign of this second derivative to the left of this point x equal to 0 and to the right of this point x equal to 0, right? Now let us take this point as -1 and let us take this point as 1. Clear? So -1 is to the left of x equal to 0 and 1 is the point to the right of x equal to 0. And let us now calculate the sign of the second derivative at these 2 points. So f double prime at x equal to -1 is equal to 12 times -1 whole square, and this is equal to 12, right? -1 square is plus, and then we find the value of this second derivative at x equal to 1, so we have 12 times 1 square, and that is equal to 12. Now viewers, here we see that the sign of the second derivative does not change when we move from -1 to 1 through x equal to 0, because here we have positive sign and here also we have positive sign. Here whenever we calculate the second derivative, we are not interested in the numerical value, we are interested only in the sign, right? So here we see that at x equal to -1, the sign of second derivative is positive, and at x equal to 1, the sign of the second derivative is again positive. So here we see that the sign of second derivative of f does not change when we move from -1 to 1 through x equal to 0. So here for this function x equal to 0 is not a point of inflection, right? Is not a point of inflection, and this is quite evident from the graph, because inflection points are points where the function changes concavity. Now here we see that this is the point x equal to 0, and we see that the concavity of the graph does not change when we move from -1 to 1, right?